Okay, most of the time, the purpose of our inverse matrix, basically, we want to solve the system of linear equation lah. Okay, when you are having system of linear equation, okay, and then you convert into matrix form of ax equal to b. Okay, and then you may use inverse to solve that system of linear equation. The most important, if you want to use inverse matrix, the determinant of your matrix must be, okay, your matrix original matrix must be not equal to 0. Okay, unless if you are getting determinant of matrix, okay, equal to 0, you cannot apply this inverse matrix. You have to apply another matrix. Okay, because inverse matrix just applicable when your determinant is not equal to 0, to avoid any singularity lah. Singularity here means that you cannot solve the problem. Okay, so you can study lah. Okay, you can go through the details of your motivation of your inverse matrix from your textbook. Okay, or even you can refer to any other references lah. The one that I want to highlight here is just regarding to, okay, some remarks lah, some remarks. Okay. Alright, inverse matrix. Okay, for example, if you are having A multiply to any matrix B, when you multiply, you are getting identity matrix. I here is your identity matrix. Obviously lah, obviously identity matrix must be square matrix. Okay, must be square matrix. So if you are getting like this, means that we can say that, okay, A is the inverse of matrix B, or okay, or B is the inverse of matrix A. Either one, because when you multiply between A and also B, so you get your identity. So you can say A is inverse for B or B inverse of A. Similar. Okay, similar. And the notation obviously lah. Okay, inverse. If we are writing inverse, so we are using power of -1. Okay, for matrix, if you are having power of -1, that's represent inverse matrix. Okay, so we have some remark here. Okay, so the first remark, if you are having A, B inverse, this is not similar as A inverse, B inverse. Remember, and this is not similar. Whereas, okay, number one. Whereas A, B inverse, that is actually B inverse, A inverse. Okay, as I mentioned in our multiplication, okay, the position of your matrix very, very important when you apply the multiplication operation. Okay, when you multiply between matrices, the position of your matrix very important. Okay, it's not all the time when you are having B inverse multiply A inverse, just similar to A inverse multiply B inverse, for example. Okay, but this is from our inverse. AB in bracket inverse must be equal to B inverse first and then following by A inverse. It's not A inverse B inverse, remember. Okay, and the second thing that you should know here is the one that I mentioned lah. Okay, a square matrix A, A. So I'm using another symbol. A square matrix B lah, for example, has an inverse if and only if. Once again, IFF, if and only if your determinant of matrix B is not equal to 0. Okay, this is the one that I explained just now. Okay, for our inverse matrix. All right. Okay, so how can we find our, okay, in order to get calculate lah, calculate the inverse. We have several approaches. Okay, similar as our determinant. So determinant, you are having calculator, you have the formula, you have the coefficient expansion. So that's also applicable. Okay, the same, not the same approaches lah. Okay, we have several approaches lah for calculating inverse. The first one, calculator, of course. Okay, go back to the same matrix here. Okay, now how can we use our calculator calculating the inverse? Okay, similar. Okay, you please okay, using your calculator, you key in, okay, what we call it, store your matrix in the calculator. Since we start already, okay, our matrix, so I just want to call back. Yeah, still over there. All right, okay, still over here. Okay, so follow the previous step lah. Okay, step in our what we call it, determinant and determinant, how to store the matrix. Okay, let's say, okay, we have our matrix inside our calculator. So to calculate this inverse, just simple. You press shift and then you press number 4. Okay, shift number 4, and then you select your matrix that you want to calculate the inverse. So let's say, so number 3. Okay, you choose matrix. They will ask you A, B, C, which one. So just now we store matrix A. So we press number 1 lah. This is matrix A. Okay, number 1 matrix A. So when you press matrix A, they will come out matrix A in the screen. Okay, and then press this button. This button of okay. This button just okay, below of your mode. Okay, mode button, below your mode button. Okay, X inverse. So now they will come up with like this. Okay, mode A inverse, and then now you can press equal lah. Press equal. Okay, you will get your solution. Can you give me your solution? A inverse. What is it? What is your A inverse?
Sir, is it 7/9?
Give me fractional number. 7/9. It's not just one, eh? You can see over there, there is this the right arrow and also bottom arrow over there. So please press right first. Okay, 7/9, and then
And then 1/9.
are you sure 1/9?
Yeah. Wait. I think. Wait.
-1/3.
Yeah, -1/3. This one similar as mine. Okay, and then
1/9.
okay, maybe your 1/9 is here. Okay, and then
-2/3.
Proceed.
1.
1.
Okay, next.
1/3.
1/3. Negative.
-2/9.
Then
2/3.
Mm-hmm.
And last one, 1/9.
1/9. Okay, so this is your inverse matrix. And remember, during the exam, normally you have to calculate your inverse matrix manually. Okay, but you may compare your final answer, okay, using your calculator. Okay, calculator just for checking. If they ask you to calculate the inverse using specific techniques, so you have to follow that instruction lah. Okay. Okay, this is number 1. Okay, we can use calculator. Okay, perhaps you are able to get the same answer as mine lah. Okay, and then number 2. Okay, we may use adjoint method. For this adjoint method, we need the help of our cofactor. Cofactor is not cofactor expansion. Cofactor expansion for calculating determinant. Cofactor we may use or apply in any other purposes lah. Okay, adjoint method. So adjoint method you learned before, okay, which is we are having the formula. Okay, for this adjoint method, basically to calculate or to find our inverse matrix. So A inverse just using this formula. Divide by determinant of matrix itself, okay, matrix A lah, and then multiply to your adjoint. What is the meaning of your adjoint? Adjoint here means that you are actually having the cofactor matrix transpose. This is transpose of your cofactor matrix transpose. So means that you have to find your cofactor matrix first. Okay, cofactor matrix. What is the meaning of cofactor matrix? If your size of matrix is 3 by 3, so means that you have to find C11, C12, C13, C14, and C21, C22, C23 until C33. That's what we call it as cofactor matrix. And then after that, you transpose your cofactor matrix. That's represent your adjoint here. And this is also the reason why we are having our remark. Okay, you see here, the square matrix has an inverse if and only if. Okay, our determinant of our matrix not equal to 0. Okay, here support that remark. Why? Because if your value of determinant here 0, you are having whatever matrix divided by 0 still undefined. Okay, that's why you cannot find the inverse if your determinant 0. Okay, this is support our remarks, second remark over here. Okay, so now go back to this one. So I'm using the same A lah, because to save our calculation, it's a several calculation. Okay. Okay, previously we calculated already our determinant. Okay, so determinant of matrix A here is -9. Okay, I'm not showing the calculation again because we did before. Okay, just we want to find our cofactor matrix. Okay, this is the one that you commonly, I think, practice before, Cij. Okay, Cij, so you are calculating C11, C12, C13, C21, C22, C23, C31, C32, C33. And again. Okay, when we are calculating cofactor, we are having formula -1 power of I plus j multiply minor ij. Okay, means that supposed to be you are having -1 power of 1 plus 1. Okay, that is d11. -1 power of 1 plus 2, d12. Okay, minus 1 power of 1 plus 3 d13, and then you follow lah for the rest. Same goes to here, here. Okay, I'm not writing the whole formula lah. Okay, so you may write by yourself. Just the one that I want to highlight here. Okay, regarding to your minus 1 power of I plus j here. Okay, so if you refer to this power, basically they are referring to the position of your elements here. So to simplify your calculation, basically you can just give us the value here, okay, based on this location, okay, your position. So minus 1 power of 1 plus 1, that's supposed to be positive lah. So you get just d11, positive. Okay, minus 1 power of 1 plus 2, odd number, so means that negative. Okay, power of 4, even number, positive. Okay, 1, okay, plus, minus, plus. And then proceed, 2, 1. 2, 1 is odd, so negative. Okay, and then positive, negative. Because 2 plus 3 is 5. Okay, and then positive, negative, and back to positive. Okay. I think this is your practice before. Okay, you consider plus, minus, plus, minus, plus, minus. Okay, basically plus, minus come from the formula of your cofactor. Okay, it's not just that, is must be plus, minus, plus, minus. So I just worry if you are having 2 by 2 or 4 by 4 matrix, you just apply plus, minus, without notifying okay, the purpose why you are getting plus, minus. Okay, basically come from your definition of cofactor. Okay, cofactor. Okay, so that's why at the end you just calculate lah determinant of your submatrix D11. Do we have D11 before? What is our D11?
-7.
-7. You calculate lah by yourself lah. But it's too far. I need to copy this one. I want to put it here. Okay. So maybe I put it here. Okay, put it down here, where is it? Okay. Okay, you can put plus. Okay, and then you multiply lah. Okay, 1, 1. So 1, 1 is you eliminate first row, first column. So that is actually 5 minus 12. So -7 just now. Okay, minus. Okay, minus. And then we eliminate first row, second column. What is it? What number minus what number? Eliminate first row, second column.
0 minus
0 minus?
6.
Sorry?
0 minus 6.
0 minus 6. Okay, because you eliminate this and this. Am I right? 0 minus 6. Minor is calculating determinant of your submatrix. Okay, plus. Okay, 1, 3. What is it? 0 minus?
0 minus -2. Plus
Okay,
2.
so plus 2 lah. Alright, proceed. Minus. Okay, 2, 1. Eliminate second row, first column. 5 minus
8.
8. Good. Okay, plus 2, 2. -5. Minus
4.
4. Okay, and then minus here. 2, 3. 4 minus?
Plus 2.
Plus 2. Okay, right. Okay, proceed. 3, 1. Negative 3
+2.
plus 2. Okay. 3, 2. 3, 2. So 3 minus
0.
0. Okay, good. And the last one, 3, 3. Minus 1 minus
0.
0. Okay, and then you calculate lah. You calculate, okay, you calculate that is actually positive negative 7 lah directly. Here negative 6, don't forget multiply negative outside here, so become positive 6. Okay, this is 2. Okay, 5 minus 8, negative 3, negative become positive 3. Okay, this is negative 9. This is negative 6. Okay, negative 1. That is negative 3. And this is negative 1. Okay, now this is your cofactor matrix. We just obtained our cofactor matrix. Okay, but don't forget, if you wish to calculate for inverse, we require cofactor matrix transpose. So if transpose means that we will change the position. Row now become our column in transpose. Okay, so now, okay, just maybe we proceed to A inverse directly lah. Okay, 1 over determinant A. So cofactor IJ transpose. So that is negative 9. Okay, our determinant of matrix A is negative 9. Okay, and can you okay, tell me one by one your cofactor transpose here? Cofactor matrix transpose. What is it? Row first. Negative 7.
3, negative 1.
Okay, and then proceed.
6, negative 9, 3.
All right. And then the last one.
2, negative 6, negative 1.
Right. Okay. So you get like this lah. Okay, and once again, if you are having scalar, this is actually just a scalar. But in terms of fraction, okay, negative 1 over 9 actually. And then when you want to bring inside, you have to multiply all of the elements to this constant scalar. So that we get 7 over 9, negative 1 over 3, that is 1 over 9, and negative 2 over 3, that is 1. Okay, that is 1 over 3. Okay, that is 2 over 9 negative, positive 2 over 3, and the last one, 1 over 9. So you can compare lah to your inverse that you calculated using calculator. Okay, 7, negative 1, 1, negative 2, negative 2 over 9. Okay, 2 over 3, 1. 1 over 3, 1, 9. Yeah, similar lah. Is it similar? Sama tak?
Yes, sir, similar.
Okay, should be similar. If you are getting incorrect solution, as I mentioned, okay, once you get your inverse using, for example, adjoint, okay, because involve a lot of calculations here, okay, okay, at the end we don't know whether this is correct or not. You may check using calculator. Okay, calculator you just for checking. Okay, if they ask you to calculate inverse using adjoint. Okay, so you may check lah. Okay, maybe from there you can detect lah. Maybe this is incorrect, for example. So why this is incorrect? You have to check back your calculation. Okay, that's how we basically do the checking. Okay, to avoid at the end you are providing incorrect solution, you will lose your marks over there. Okay, so any question for calculating inverse using adjoint? I think this is the one that you learned before, isn't it? You learn how to calculate inverse using adjoint. Am I right?
Yes, brother.
Okay. Any question? May I proceed?
Yes, sir.
No questions, sir.
Okay, so we proceed to the last methods in calculating our inverse. So number 3, we call it as elementary row operation. Or simple say arrow. Okay, maybe some of you learned before. Okay, this elementary row operation. Okay, but some of you maybe you just heard this one first time lah. Okay, heard this one. Okay, so I just want to remind you. Okay, in our arrow, so we just having 3 methods or options to perform this elementary row operation. Okay, 3 step lah. 3 allowed step. Okay, the first one. Okay, so remember when we are using arrow, all is about row. There is no column. Don't ask me, okay, before your exam, can we use this operation between column? Cannot, because the name actually row here. Means that all operation must be involving row only. Okay, remember, So now our step here also involving row only. Okay, first, you may change your row 1 with your row 2. For example, your row 3, you change to your row 4. Okay, this is what we call it as interchanging. So I'm not using this. Interchanging I row with J row. So now J here is not column, just notation. Okay, because we use just one notation, means that this is just row I, row J. Okay, if you are having this notation, means that you may interchange, okay, I row with J row. Okay, just change the position. For example, row 1, you interchange to row 2. So all element in row 2, you put it as row 1. All element in your row 1, you put it in row 2. Okay. Okay, just a moment. Okay, sorry. Okay, that's the first one. Okay, the second one is multiplying row with scalar, constant. Okay, for example, K multiply Ri, for example, or Rj, doesn't matter, similar, just to represent our row. So K here is your scalar, or constant, constant. So here means that we multiply I row, okay, with constant K. Means that all element in your row I must be multiplied to constant K. For example, you are having here, okay, let's say here, you want to multiply row 2 with constant 3. So now become 18, negative 27, and also negative 9. All element must be multiplied to that constant K. And the last one, okay, you want to do operation plus or minus. Okay, so between two rows. Okay, for example, row I, okay, plus lah. I'm using plus lah. Okay, plus beta, row J. But here we have here H and K. Okay, once again, H and K can be any constant. Before that, I would like to remind you, constant here K cannot 0. Cannot 0. Other than 0. Positive possible, negative value possible, but not 0. Not 0, remember, not 0. Okay, same goes to this H and also K. Okay, constant H and K means that your I row is multiplied to constant H. Okay, and or basically not minus lah. Minus can be from K lah. Okay, J row is multiplied to constant K. Okay. Why I'm using just plus? Because as I mentioned, K here, K constant here can be positive or negative. If K here is positive, means that you have addition. If K here is negative, you have subtraction. Okay, that's why I'm using just plus. But the one that I want to highlight here is regarding to K. It doesn't matter either whatever your constant here. Your constant can be 1, can be minus 10, can be any numbers other than 0 once again. Other than 0. Cannot 0, remember Cannot 0. And the most important, this addition must be in between rows only. You cannot row 1, okay, you minus to column 1. Cannot. Must be in between rows. Okay. And also, you cannot okay, remember, you cannot add row I with just a single constant. For example, row 1 you add 2, cannot. Must be you add to another row. Okay, row 1 plus 2 row 2. This is okay, no problem. Cannot you just add any row to just a constant? Cannot. Okay, remember this is common mistake if you are not understanding this arrow. Okay, okay, so we are having just 3 steps here. Okay, before I proceed to to go back to this one, okay, inverse. So I just want to highlight here regarding to what we call it rank, okay. Rank of a matrix. Okay, rank of a matrix means that, okay, you just calculate how many number of non-zero row in your matrix. Okay, in simple word, the number of non-zero row, okay, in your matrix, and the most important, your matrix here epsilon matrix or reduce epsilon matrix. Okay. To get your rank normally we use the symbol P. Okay, P. If your matrix is matrix A, A lah, PA. If your matrix is B, PB. Okay. Later we use this notation P to represent our rank. Okay. Rank here is just, okay, number of non-zero row in your matrix, but your matrix here must be in the form of epsilon matrix or reduced epsilon matrix. What is the meaning of epsilon matrix and reduced epsilon matrix? So we go for epsilon matrix first. Okay, epsilon matrix here contain one, I think 5. Okay, 5 items that you have to check. From your matrix, either you are having epsilon matrix or not, you have to check these 5 conditions. Okay, the first one. Okay, the first one, your matrix must be has at least a non-zero row. Okay, so means that you cannot having zero matrix lah. Zero matrix is not epsilon matrix. Okay, null matrix is not epsilon matrix because at least a non-zero row. When we are saying non-zero row here means that, for example, 0, 0, 0, 0, 0, 0, 1, 2, 3. So we are having one non-zero row. So this is enough, okay, to be part of our epsilon matrix. But yet you have to check, okay, another condition. Okay, same goes to, let's say, if you are having 0, 0 here, but 3, okay, the last element here 3, still considered as non-zero row. Okay, when we are saying non-zero row, at least an element in that row is not zero. At least, okay. So for this non-zero row means that at least an element in this row is not zero. Okay, at least one element in that particular row not zero, considered as non-zero row. Okay, that's number one. Number two that you have to check is regarding to, okay, the most left, okay, non-zero element of each row is 1. What is the meaning of this? Okay. Okay, this is when we are talking about non-zero row. Okay, non-zero. The most left non-zero element of each row. Each row here referring to non-zero row. Okay, so we are talking about non-zero row. It's not zero row. Zero row is just let it be zero row. Okay, now we are talking about non-zero row. The most important, the most left non-zero element. So we go for element in this non-zero row. For example, just now. Okay, we are having this non-zero row. And between these three, okay, we just consider non-zero element to be part of this condition number 2. Okay, so we are having 1, 2, 3. Obviously, all 3 elements here non-zero element. Okay, and between these 3 non-zero element, the most left element must be 1. So the most left should be 1 here, and that is actually 1. So this is also another part of our epsilon matrix. I give you another example. Okay, another example 0, 2, 5. 0 to 0 lah. Okay, and then 1, 0, 3, and here 0, minus 1, or maybe just 0, 0 lah. Okay, how many non-zero row that you are having in this new matrix? How many non-zero row?
2.
2. First and second. Now, for first row, we consider non-zero element. How many non-zero element in our first row? How many non-zero element in our first row?
1.
1, just 1. These 2. Okay, we not consider 0, we not consider 0 because here we consider just non-zero element. So now take a look. 2, since the only element non-zero in this first row is 2, so here 2 must be actually 1, cannot other than 1. So this is must be 1. So you are having problem here. So this is not satisfying our condition number 2. How about row number 2? Okay, so non-zero element is actually 1 and 3. So once again, we are not considering this 0 because we focus for non-zero element. So 1 and 3. And between 1 and 3, the left element is actually 1. Okay, and this is already 1. So this is no problem. Okay, this one also, okay, the first example here, no problem. So this is how we understand the second condition. Any question for the second condition? Understand? Understand?
Yes.
Okay. Number 3. Okay, before I proceed, okay. So if you are having the most left non-zero element of each row is 1, okay, the most left here. So this element we call it as pivot, pivot. Okay, pivot. So this is our pivot. This is our pivot, but 2 here not pivot. How can we make it to become our pivot? Yeah, you just perform arrow lah. Okay, means that here we multiply to 1 over 2. Okay, in other words, we divide by 2 lah. Divide by 2 is just similar to multiply to half. Similar. Okay, and then you are getting 1 here and becomes your pivot. Okay, so pivot so I'm using pivot term here. And elements. Okay, all element okay under your pivot okay must be 0. Okay, for example, okay, we take this 0 0 0 0 0 0 1 2 3. For this case, this is your pivot. Okay, the most left is 1, that is your pivot. But since this is your last column, so obviously there is no any other elements under below this pivot. So this one all automatically satisfy the third condition. So let's say we proceed to another example here. 0, okay, let's say I'm making 1. 1 0 3 0 0 0. Okay, let's say like this. Okay, so for the first row, this is your pivot because this is the most left, but the only elements lah, not 0. Okay, and 1, this is your pivot. Okay, for the second row, this is your pivot. So means that each row contain their own pivot. Okay, if that is considered as non-zero row lah. Okay, but for the third row, there is no pivot lah because that is 0 row. So pivot here. And the most important, you have to check all elements under this pivot. Okay, okay, this is elements below this pivot, 0. Okay, this pivot element, all elements 0 here, no problem. Satisfy our condition number 3. That's the meaning of all elements below the pivot must be 0. Okay, number 3. Okay, number 4. I just finished this one. Okay, pivot on the upper row must lie on the left of the pivot on the row below it. Okay, now we are talking about position of our pivots. Okay, so for example here, okay, this one. Okay, we know that the first column, the first row, this is our pivot, and the second row, this is our pivot. Now we compare the position between these two pivot. Okay, first row pivot and second row pivot. Okay, they mentioned that pivot on the upper row must lie on the left. Okay, if we are referring to this current matrix, one here is positioned on the right of this second pivot, second row pivot. And this is not satisfying the condition number 4 here, because dimension must be located on the left of the pivot below it. Okay, below it. So this one not satisfying the condition of number 4, because pivot first row on the right of pivot second row. So how can we make it satisfying this condition number 4? We just interchange the position. So let's say I'm using this row 1 interchanging. Alright, so this one, row 1 interchanging row 2. So if we interchange 103 010 000. Now take a look here. This is your pivot. This is your pivot. So we compare the position. Okay. Now when you see this position, pivot of the upper row now located on the left of pivot located, okay, a row below it. Okay, the second row lah. So for this one, this is satisfying our condition number 4. Okay. But of course, you cannot having the same pivot on the same not the same pivot. You cannot having the same column for the pivots. Okay. For example, like this. For example. Okay. So this is your pivot. This is your pivot. They cannot share the same column. Must be strictly on the left. Okay. If far away, okay, this one cannot. If far away, no problem. Like this. 10, okay, 100001. Okay, the most left is 1. Even though here we are having 1 also, no problem. But the most important, this is the most left and must be 1. This is your pivot for first row. It's not the second one here. Okay, and the second row, this is your pivot. So if we compare the position, this one still on the left, even though this is yeah, okay, you are having the gap is maybe two more columns lah, the distance here. So between this pivot down here, it's okay as long as on the left, no problem. So for this one, this is okay. All right, understand number 4, condition number 4? Understand? Class?
Yes.
All right. Okay, the last one, the most bottom the most bottom row can be all 0. The most bottom row. Rows. Okay, this one simple lah. Okay, means that the last row here can be all 0 lah. Can be all 0. You can place, okay, for example, here, okay, your, what we call it, your first 2 rows are 0 rows. Okay, so you interchange the position, you make it your third row here become your first row, and then now you are getting like this lah. 1 2 3 0 0 0 0 0. Okay, these two can be all zeros. Okay, that's number 5. So if you are having this 5 condition, that is actually your excellent matrix. Must satisfy all 5 condition. Cannot just satisfy first condition, but the rest not satisfying. So that is still not yet excellent matrix. You have to do something. Why is it? Arrow lah. Okay, so I just I think I stop here. So we continue this part of arrow in our next class.